I welcome you all to this course on diffraction and imaging. Okay. In the last few classes I had covered the different modes of diffraction, okay, like parallel beam diffraction, convergent beam diffraction and divergent beam diffraction, and some of the applications. Okay. In a microscope, apart from getting diffraction from different regions of the sample, we can get information about the how the image itself looks like, right, in addition to diffraction. So, how the contrast arises in the microscope, okay, that is what we will discuss about it. Okay. Earlier itself I mentioned that in crystalline material the contrast comes from or we call it as a diffraction contrast. That means that whatever the diffraction phenomena which is occurring is responsible for the main contrast mechanism. Okay. So, essentially we have to use the formulas which we have derived for finding out contrast from different regions of the sample. Okay. That is what has to be done, and this is one with respect to a perfect sample, and mainly the contrast arises in a perfect sample if it is a polycrystalline material. From one region to another region, orientations could be different, the extent of scattering could be different, that will give rise to a contrast. And if it is within a grain, various types of defects which are present, they would also bring about displacement of atoms from their normal position, which will give rise to contrast. So, these are all the various types of defects, this which I have mentioned long time back. Okay. So, I am not going into it. So, essentially when we have a sample like this and all the planes are arranged like this, if you consider a beam which is entering like this and when it comes out, okay, as the beam passes through the sample, this may be consisting of many unit cells arranged one on top of the other. So, if there is a so even if it is a perfect crystal, if there is some scattering which is going to take place from every depth, okay, into the diffracted direction, the amplitude of the wave which comes out is going to be different, right. So, depending upon the composition, okay, suppose this region contains ordered alloy, another region contains a disordered alloy. So, the extent of contribution to the scattered wave will be different in this region and maybe from this region. So, there will be a variation in the intensity of the transmitted beam itself. So, if you look at the back of the sample, what essentially we get it is a variation in amplitude of the transmitted beam which is transmitted in this particular direction, the same as the direction in which the beam has entered. Similar to this, okay, in the scattered direction also there will be variation is going to be there. Okay. So, this variation if we see it in the transmitted beam alone and try to magnify it by using lenses, then we are able to get some variation in contrast. That is what we call as that image, right. That is what we normally do. Okay. So, this we can understand it in a way that when the beam and incident beam enters, okay, this is the direct beam and there is a waves which are scattered in different direction, okay, and we have derived earlier expression for finding out the intensity of each of the amplitude of each of the diffracted beam and also its intensity, right. That is under a kinematical condition. Okay. What we will do it is now we will go back and extend it further. Okay. So, the total amplitude, okay, in a particular scattered direction essentially depends upon the intensity which is scattered in that particular direction from the full volume in which full volume of the sample which is illuminated by the electron beam, correct. That is, if an electron beam is falling onto the sample like this, okay, this is essentially the transmitted beam, and you see that from this region diffracted beam is going to be there. Okay. If you put a lens, what the lens does it is, at the back focal plane all these rays are focused together, okay. So we get the diffraction spots, but since the diffraction spot is a concentrated one, we are not able to see the variation in intensity there, right. But if that same area which is there is magnified and we see it in the image plane, so the image plane we are able to see the contrast which arises, okay. But essentially what we see it is nothing but the variation which has taken place because of the diffraction which is occurring in a specific direction. So many directions it will be taking place. Normally when we do microscopy, we use a technique which is called as a two beam condition, that is a transmitted beam and a diffracted beam. That means that the sample is tilted in such a way that only one particular planes are strong oriented for strong diffraction, okay. So if we consider that, then we know that every atom position which is there, that volume can be taken as, okay, one corresponding to a primitive unit cell plus the one which corresponds to primitive or a non-primitive unit cell, that is as one cell, plus one which corresponds to the atom positions in the unit cell, plus this corresponds to a position which is the, if a defect is there, in the defect there is a slight displacement of the atom from that position. This is what it tells about the atom positions in the and this finally the expression which we have derived earlier is one which it corresponds to within the unit cell, which we call it as the structure factor, and the whole volume which we consider is essentially the shape factor. This together gives the amplitude of the each of the scattered diffraction spot which will be coming, correct. Okay. Then we have derived this expression, that is the structure factor. We know that for every unit cell it is going to be the same, okay. But the shape factor turns out to be, okay, this sort of value will come sin pi, okay. And if you look at it, how this shape looks like, okay, this is how the shape is, and here we can make out that away from the exact Bragg condition also there is some intensity which we can see it, okay. So that condition we normally write it as delta k equals that as G plus S, right. Essentially this is equivalent to, suppose diffraction spots are here like this, okay. If the Evalds sphere passes through two spots together, then we say that there is no deviation, exact Bragg condition is satisfied. If the Evalds sphere is slightly tilted, okay, then what we can do it is from here to here, this is G, this is the delta k from here to here, this will be G plus S, and that sign depends upon how we have fixed the coordinate, okay. So instead of this delta k, if we substitute this is an expression which is a general one, but x, y and z direction this will have components. So this is what the expression for the shape factor turns out to be, okay. The total intensity, if you look at it, this multiplied by the structure factor will give the structure factor squared will give the total intensity, okay. And when we put G plus S, okay, then what is going to happen is that G dot A, because A is a lattice translation vector Ax. So if Gx plus this one, if you take it, that is a integer, okay. So because of that, what is going to happen is that all these terms, okay, that only the S will come into the picture, the other factors will not be there. Here what we have considered, S is equal to, the vector is written as I into Sx plus j into Sy plus k into SZ. Okay. But normally in microscopy one assumption which is being made. The assumption is that okay, the deviation in the Bragg condition is only in the Z direction, other directions the deviations are 0. Okay. If we make that assumption, then when Sy and Sz become 0, then what this term will turn out to be? Will turn out to be that ny squared and nz squared, right? Because from the hospital rule this will, okay. So only this term which is going to be there, correct. So this will be the amplitude which it will give. Okay, this term which is because when a scattering takes place from a particular point and the intensity we are measuring it at a point which is far away r, then this will give e to the power of 2 pi k dot r by r will come, okay. And this is divided by the volume of the area. If you take it per unit volume, you will be getting this amplitude. So amplitude squares give the intensity, correct. And intensity of the, if it is a 2 beam condition, intensity of the transmitted beam will be I minus Ig, okay. This is all along a particular value of that is for a specific value on x and y, that is that we are doing it, okay, right. Because this intensity, if you look at it, this Az into n will turn out to be T. So this is the expression which we will get it, okay. This is along the sample, along a particular column which we are doing this calculation. So with respect to a coordinate system which you have chosen, this may have some value of x and y and z. So like that we can say another x and y value we can have it, and along this column z we can find out what the intensity is. This is how an intensity has to be calculated to find out how the contrast is going to come, is it not? Okay. If we do that, essentially we get a mapping of that intensity at the back of the sample. With respect to a transmitted beam we can find out. Similarly with respect to the diffracted beam also. Is that clear? Okay. So that way we can find out the intensity distribution. There is another way in which it can be done. That is because when we look at the scattered intensity, okay, with respect, this is sigma into Rg, okay, over the various unit cells which are there, Fg into exponential 2 pi S dot Rg which comes. R is the position of that x, y and z position, okay. Essentially in a wave we are adding the various waves, right. This is mathematical way in which we can do it. There is a graphical way in which we can also do it, okay. In a graphical representation what we do it, since this is a complex one, okay, the real part and in a complex plane this can be represented as an amplitude and an angle theta we can represent it, correct. That way also we can represent, okay. If we represent it that way, okay, then from here when it comes something has been scattered, okay, amplitude, then if you see from here the position of R is changing, right, as we go along this column. That means that here R0 xy, it's xy z0 you consider origin, z equals 0, then the z value is going on changing it. That means that this phase term is continuously changing. This phase term changes, the change in phase term is equivalent to change of this angle theta, e to the power of I theta. So now we can plot this as an amplitude phase or a phasor diagram, right. That means that this is the first wave at the top, the next one, so like that it comes. And now if you see the resultant amplitude, this gives the amplitude of the wave, right. This is one, this is another way in which we can look at it, okay. Is this clear? Because one we have calculated using the mathematical expression which is there, directly found out that intensity. Another is along that column using this phasor diagram also we can find out what is going to be the amplitude and what is going to be the angle theta, which we can find out. Okay. And then this is, suppose we assume that this is the net amplitude of the scattered wave. Okay. Then if you have to find out the intensity, the psi star has to be taken. That will always be, if you take it, it is going to be, the intensity is going to be in the real always. That is, it is going to be in the plane which is going to be in the real plane or the x axis plane, right. The y axis plane is the imaginary plane when we consider it. Okay. So this is what it gives, that intensity. So irrespective of what the orientation of the amplitude, orientation of the wave, okay, in the complex plane, if you look at what the intensity is going to be, that does not depend on that, correct. Okay. This has some consequence. The consequence essentially is that expression which we have derived, okay, it contains e to the power of 2 pi I s into z, okay, or s into t for the thickness of the sample into fg, the phi g will be equal to, okay, into s into over that full region. If you see it, it will be an integral which will come into z into dz, it will come. Okay. Otherwise it can be written as over the full column we have added that also, that term, correct. Both the ways we can represent it. The other expression which we have to, okay, I think I will come back to that later. Okay. Suppose the value of s is very large, or the value of deviation is very small. What will be its effect on the phase? The phase factor, if you consider, if s is for a s into r, if we r s into z, if we take it, if s is small, this term is going to be a small value, right. So the angle theta is going to be rather small, correct. So if we take that way, that is what we are trying to do is that the beam is falling on that sample, but it is not at exact orientation, but there is a small deviation, s is there, but it is very close to the Bragg orientation. Okay. In such a case, what is going to happen is that if you look at the net amplitude which is going to be there, is going to be rather very large, correct. And there is a problem which comes in that, because kinematical theory is based on the assumption that only a very small intensity is getting scattered, amplitude turns out to be large. Then when we try to calculate intensities, they can turn out to be 0. There are a lot of problems are going to be, it does not explain the results also correctly. Instead, suppose the value of s turns out to be very large, okay, then what essentially is going to happen is that is if it is g, that is, let us consider two values of s, s1 and s2. S1 is close to, so the intensity of the or the amplitude of the scattered wave is going to be very large here, whereas here compared to the intensity which you should have at exact Bragg orientation, the intensity is going to be very small for this value. That means that this corresponds to a condition where the amplitude of the scattered wave is much small compared to that of the incident wave, right. So the kinematical theory is valid in this case. Here how it happens is that when that is very large, since the angle theta, what will be the effect of this large s? Because for the same z, s into z is going to turn out to be, the phase angle is going to be large. So when the phase angle is large, even for the same, it will be, one will be coming like this, another will be coming like this. For a few vectors, this can go like this can move around in a circle, but overall the amplitude is turning out to be very small compared to the original amplitude of the incident wave. So in this condition, okay, we will have the kinematical theory is valid. Okay. What will be the consequence of it, which we will see it in two cases. Okay. In this expression also, what we are writing it 2 pi I, because that intensity when we write it, it is sine squared pi s into t. Okay. Intensity of transmission is proportional to here, correct? This is the sort of an expression which we have. For a particular value of S, you can have a value of t so that this term turns out to be an small integer, correct? Then what will happen is that the intensity will become 0. Depending upon that value, the intensity can fluctuate, correct? So, it is for the same value, that for a particular value of S, we have multiple values of t for which the intensity can go to maximum and come down to minimum. Okay. That is what essentially is being shown here. Suppose we have a wedge shaped sample, the same parallel beam is falling onto it. Intensity of the diffracted beam, if we try to look at it, okay, for this particular thickness, okay, this is using the phasor diagram, it has been shown, but essentially what we will see it as we go at that is that intensity becomes 0, it reaches a maximum value, okay, then it becomes 0, it fluctuates like this. Okay. Opposite effect we will be seeing it in the case of a intensity of the diffracted beam, or in the bright field and dark field we will be getting complementary contrast, correct? And as per this, if S becomes small, what it will happen? The thickness has to be at a larger value, the separation at which this from bright to dark and bright to dark, this fringe contrast will change. So, that means that this is how it will go. Suppose S becomes 0, what happens? Uniform intensity. There should be uniform intensity. That is what kinematical theory says. What is it seen in practice? That is not the case. There is a variation. Okay. Here, this is with a large S. When we see that it is a bright field micrograph, closer to the end of it you can see some fringes, okay. And this is in the dark field, you can see complementary fringes could be seen, it is taken from the literature. Okay. The same sample, when it has been taken to S equals 0, you see that the fringes are still seen with a large width, bright field, they are much better contrast. Okay. This is what the observation is. That means that though the kinematical theory is able to explain some of the features under some conditions, it is not able to explain completely all the features which we observe in the microscope, especially when a strong diffraction is occurring. Because when we say that S equals 0 means that it is satisfying the strong diffraction condition. Okay.
So why are you saying positive S does not satisfy kinematics?
No, not positive S, I am telling. Yes, when it becomes 0, this is the expression which is derived now. When S becomes 0, what it says that is, it has to be only uniform intensity, but that is not what is being seen. So, that means that there is something is wrong with the theory which has been developed. This is valid only for when we have this theory can be applied only because when S is small, okay, or the S is large, the deviation from the Bragg condition is large, okay, the intensity of the diffracted ray is much smaller compared to that of the transmitted. When the intensity of transmitted and the diffracted beam become very close to each other, that takes place under the condition when S becomes equal to 0. Under that condition, this theory is not able to explain the observed contrast. So, we have to develop a theory which that theory is called as the dynamical theory of contrast.
So this theory does explain
when S is large, it is able to explain,
Yes.
but when S is equal to 0, it is not able to explain. That means that under all conditions it is not able to explain the contrast.
So
You
when
understand?
S is 0, we are getting the large quantity.
The S equals 0 is what we are getting it. By theory there should not be any fringe contrast, but now you have a fringe contrast. Okay. Essentially what happens is that the dynamical theory also gives an expression which is equal to sin squared pi, it will be written as S effective into T divided by pi S into A the whole squared. It's all will be turning out to be the same. Only thing is that the S now which is written as S effective equals root of this S squared, the deviation from Bragg condition, by 1 by psi g squared it will turn out to be. Okay. This we will come to it, how this expression is being derived. I will not go into a full detail of it because it requires a great deal of understanding of condensed matter physics. We have to go through it, which will not do it. But what happens is in this, when S becomes 0, still the S effective is going to be 1 by psi g, correct? So this term never becomes 0. You understand that? That is why it is able to explain. Okay. Is it clear? Okay. So far what we have considered, all the amplitude derivation which we have looked into, we have not taken the absorption of the beam as it passes through. That is as if that only the phase is changing, there is no other change. But if there is an absorption, absorption is, what do you mean by absorption? It is essentially is that if any inelastic scattering is occurring, okay, the primary beam is lost. So all these things contribute to the reduction in intensity, reduction in amplitude of the wave. Okay, that we call it as an absorption. Okay, if that happens, then in the same phasor diagram, every time as the beam enters into the sample, okay, gradually the absorption is also going to increase as it passes through the sample. That is as Z increases. Okay. That effect will be, that amplitude will be reducing, but the phase remains the same, the deviation. So now if we look at the phasor diagram, it will not come back to a circle, it will be like helix, it will be just going on spiraling inward. Okay. But still that same thing could be used to explain how the variation in contrast, this is what it is being done with the number of unit cells, the intensity, how it is going to change. Okay. But now if you look at it, when the thickness is small, whatever is the variation in intensity which we see, as the sample becomes thick, the intensity variation is going to get smeared out gradually. Is this clear? Okay. Now so far we have considered the case which is for a perfect crystal, because we assumed that there is no defect which is present. When a defect is present in that sample, then in this term delta k dot RMNP, that G plus S will come into RL corresponding to the lattice, okay, then RU corresponding to each of the unit cell, okay, plus RD which is corresponding to the defect which is present at some location. Okay. Now if we just expand this expression, G dot RL is the term which is essentially going to be a integer, correct? G is a perfect translation vector, RL is a corresponding to a different lattice points which represent each different point which represents each unit cell. Okay. S is a deviation from the Bragg condition. Because of that, what we can see that this S dot RU is with respect to unit cell. Unit cell is a specific cell which we are considering it. There the RU vector is cannot exceed the lattice parameter of the unit cell. So this S, if it is small, S dot RU can turn out to be small. Similarly, RD is the deviation from the correct position of the atom closer to the defect. So that deviation is also very small. So S dot RD will also be small. Then so these can be neglected because the effect of this is close to this becoming equal to 0. Okay. G dot RL is going to be an integer. So now we will be left with only 3 terms which are going to be there. S dot RL plus G dot RU plus G dot. So
what is RA, RU?
eh?
So what is RA, RU?
RL.
Oh,
RL corresponds to the each unit cell is represented by a point, lattice point. RU is there with respect to each unit cell, the positions of atoms in the unit cell. RD is corresponding to the defect. Okay, the defect which is present at that point, it is deviated from, it is not RU, there is a small deviation is going to be there. Now that intensity for this we have to write it in expression exponential. Okay. This if you try to write it, you can see that 2 pi a, these two terms come together, this term is with respect to a unit cell. If you take summation over RU, what does this term turn out to be? Structure factor. Okay. And this is summation over the different full volume. Okay. But the way the summation we can do it is two different ways we can do it. One is the summation over the volume is you take any xy point on that sample and take along z, like that you go on integrate, do the summation. Okay. And this summation we can write it as also can be written in an integral form, because since we are taking it with respect to different depths like this in that sample, as that z varies dz. Okay. The different unit cell if they are there, we are essentially, it is a summation we are taking that can be written as an integral over the full thickness of that sample. If we write it, this will become Fg into integral 2 pi a. These are all the terms which are going to be there. This term, if you look at it, what it corresponds to? With respect to a perfect lattice, but there is a deviation from the Bragg condition. Is it not? What does this term corresponds to? Is G is the with respect to a reciprocal lattice vector, RD is the deviation from the defect vector. Is it not? Okay. At some particular position, suppose in this sample we assume that okay, at this particular region we have a defect is there, so that the lattice parameters, there is an expansion or contraction, or there could be a rotation. There are different ways in which the displacement can manifest itself. Okay. If that is what it happens, okay, and this some integration, some mathematical convenience, it is being taken from middle of the sample to minus t to t by 2, do not bother about all those. Okay. Finally, when we get the integration over z for various values of x and y, we can find out at the back of the sample how the intensity is going to vary from region to region. So, where the perfect crystal is going to be there, in those region intensity will be uniform, where the defect is going to be there, there will be a variation in intensity or the variation in amplitude will come. Okay. This is that suppose for some particular value of G, because the G is a reciprocal lattice vector, we are using one particular G reciprocal lattice vector for which the displacement vector RD is such that the G dot R becomes 0. Then what will happen? The defect will not be visible, correct? So, as if then the intensity variation is going to be only with respect to whatever is the deviation from the Bragg condition. That's what essentially this term tells, is that exact Bragg condition you get some intensity. If the beam is tilted slightly away from the Bragg condition also, you get the intensity due to the defect, but the intensity contrast varies. That is what this expression allows you to calculate. But you should remember that all this expression which we are talking about is all for kinematical condition, correct? The expression which we are using is a kinematical condition. But if this G dot RD becomes much less than 1/3, effectively the contrast is going to be very small. For all practical purposes we cannot see it. Okay. So, this is what it happens. So, with this sort of expression we can do a calculation, and that is being done also. Okay. I will come to some defects, I will take it later and show you how the defect that I will not do it in this class, and in another class we will do that. Okay. Now so far we have considered for a perfect crystal when S varies, how the intensity is varying, how to calculate the intensity at different points on the sample surface. Okay. Then when a defect is present, how the intensity will be changing, that formula we have looked at it. Using this we can calculate the defect, but specific cases we will consider. But we have seen also that this has a problem. The problem essentially is that all the experimental observations of the contrast, this theory is not able to explain completely. Qualitatively it explains, quantitatively there is a serious issue, for which we have to develop the dynamical theory. Okay. Okay. What is dynamical theory? Okay. Let us try to have some basic understanding of it. Is that if, since electron interacts strongly with matter, okay, as the electron beam enters into the material, if it satisfies the Bragg condition, as we were discussing before the class started, for the Bragg condition, electron will be strongly scattered, okay, when it satisfies Bragg condition, and from this plane it will again be scattered back into the transmitted beam. Similarly, this beam, when it is from the next plane, when it scattered, it will be scattered into. So like that, back and forth there will be a scattering of intensity is going on. But what we should remember, that when the wave is getting scattered from one to the other, always there is a factor I comes into the amplitude, correct? That is, if you take any beam, okay, a plane wave which is entering, the scattered wave, if you look at it, that intensity will be some proportional to I into psi it will be. Okay, that means 90-degree phase difference always it introduces. Okay. So because of that, in the scattered direction G, the Bragg diffraction, first diffraction when it has taken place, this I into psi 0. Then from this G, when it scatters back into the original direction, then again I into psi G will come. So this, if you multiply, this turns out to be minus into psi 0. That means that the beam which has been doubly scattered, it is out of phase with respect to amplitude. So because of that, the amplitude in the scattered direction, if you try to look at it, amplitude in the transmitted beam, if you look at it, it gets reduced faster. Okay? The same thing. So there is a particular distance at which the amplitude of the transmitted beam becomes 0. Okay? That distance we call it as the extinction distance. Okay? That distance depends upon, okay, the periodicity in that particular direction. Okay? And what all factors this, and this is called the psi G. What all factors this depends on? One, it depends upon the volume of the unit cell. That is, if the unit cell volume is large, the scattering is going to be small. Okay. So this psi G becomes large, okay, because number of atoms are going to be less. And what is Fg? That is, Fg is the structure factor. Structure factor means a structure factor for a particular scattering. If the structure factor is going to be strong and the structure factor is high, then over a short distance, okay, the intensity of the transmitted beam will get reduced. That means the psi G becomes smaller. So psi G and structure factor are inversely related. Similarly, you take the case of the wavelength. If we go on increasing the energy of the electron beam, what will be its effect on the material? It penetrates, but what happens? The scattering power gets reduced na? As it enters through it. Its effect will be that psi G will be, so this will be also an inverse relationship. So essentially the psi G can be written in this sort of a form with pi. But all these things could be derived. This is a qualitative way in which we are looking at it, but this expression is an exact expression which is derived from the dynamical theory. Okay. Now we will go into a dynamical theory just to get some brief idea about it, because this requires an understanding of quantum mechanics. Okay. Okay. Before going into it, what I will try to tell you is that psi g of the scattered wave depends upon this term. F of theta is the structure factor, correct, and sigma n, this is over the full unit cell which we have to consider. This is how phi g for each wave is going to be, right. And when an image, when we look at it, okay, at every point on the image plane, the intensity at that point depends upon how much has been scattered in each of the direction, correct. So, that means that the total intensity of the scattered beam, if we look at it, it depends upon the transmitted beam with some phase, and then psi g is with respect to amplitude of the diffracted beam and the direction in which it is coming. Then with respect to various beams, all of them together determine the total wave amplitude at every point in the image. Okay. Okay. Now, let us come back to the sample again. Okay. In a dynamical theory, what we assume is that essentially it is solving the Schrodinger equation. Electron beam with a very high energy and with a value of kinetic energy equal to particular value, which is given by the accelerating voltage, is entering into the sample. So, for that, when it is in vacuum, h bar squared by k squared by 2m will be kinetic, okay, from which we can find out what the value of k is going to be. When the beam enters into the sample, okay, the sample consists of ions which are arranged in a specific position. This gives rise to a periodicity of the potential, right. This periodicity has got two aspects which we have to consider it. That is, potential may be like this if you assume it is varying. That means there is an average potential is there over which this fluctuation is going to take place. This average potential, what it is going to do, this is a positive potential. When the electron enters into it, it is attracted towards it. So, the energy of the electron as if it is increases a little bit. So, when the electron enters into the sample, its k vector is going to be different inside the sample compared to when it is outside the sample. Okay. Then there is an interaction which is going to take place with respect to the potential, and generally the potential of the material, if you look at it, most of them are maybe 20 to 25, from maybe few electron volts to 25 to 30 electron volts, whereas the kinetic energy of the electron which is coming, if you look at the voltage which we have given, is 100 or 200 keV. So, its orders of magnitude difference is going to be there. Okay. Still, what is essentially is going to happen is that there is going to be a variation. Okay. So, in this expression, this is the, I had just taken a potential like this. Okay. This potential, how we can, because if you look at it, this is periodically varying potential, correct, but it is not a sine function, right. So, this can be written as, this periodic potential can be written as sigma, okay. We can separate into a Fourier series, we can do it with some period corresponding to g, that is, it will be this distance, if we know that 1 by inverse of it will be. So, with respect to that 2g, 3g, like that we can find out, then we can write that sigma of this one, this ug and all, for each of that wave which we consider with a particular g frequency, what is going to be the coefficient corresponding to that, Fourier coefficient corresponding to that. Plus, this is the way the potential could be represented, is it not, in the sample. Is it clear? Because since atoms are arranged in a periodic fashion, okay, as the electron beam enters into it, depending upon where it enters, it is going to see a different type of a potential. Okay. Its kinetic energy is going to change, this potential is going to be different. That psi r is that amplitude at every point is also a function of, it is written as phi g which is essentially nothing but the amplitude of the scattered beam, it will be a primary beam or the different scattered beam, into e to the power of I k plus g psi. This is the direction k in which the beam is entered. Okay. If this is the next position which corresponds to a reciprocal lattice position, okay, or the atom positions, the reciprocal lattice also will be with an inverse in this direction. You assume that this is a reciprocal lattice, then from here to here what it represents? G. So, this vector will represent the beam which is the direction in which the diffracted beam is coming. This will represent the diffracted beam coming in another direction, this will represent diffracted beam in. So, these terms are going to be essentially, that is what in k plus g over all g values. Okay. So, in each of the direction you can have a wave function which we can write it for that. It is all add, that is each corresponds to that phase factor, plus this is the one which gives, which is related to the amplitude of each of the scattered wave. Okay. That is how the total intensity. If we substitute in this and try to solve it, this is d squared psi by dx squared. Okay. One of the things which we have to keep in mind is that this g can have, k can have component kx, ky, kz. Similarly, g can also have component gx, gy, gz, correct. But what normally happens is that since the energy of the electron beam is very high, okay, and compared to the separation between the atoms is going to be small, okay, and we are assuming that the beam is falling in the z direction, then the g is almost perpendicular to r, right. So, because of that, what is going to happen, the gz will turn out to be a 0 term, only gx and g. Then if we just, this is just a mathematics, you just substitute this one, simplify it algebra, okay. That is essentially what is being done. When it is being done, we get some expression like that, d phi g by dz into I into some terms will come. This is kx, k, gx, ky, gy, kz, okay. This phi g is another, this is the amplitude of the scattered wave, plus one more term which comes, I 2m by h bar square 2 kz. This by I am not going into it, you can do all this algebra, then this will turn out to be this phi dash, phi g dash into this ug comes. That means that in this term, it is for different values of g which we are considering it. It is between the Fourier coefficients of the amplitude of the wave at every point is coupling with, is multiplied by the Fourier coefficient of the potential corresponding to each of this, correct. This is a Fourier coefficient of potential, because how we have written this expression VR ug, right. Yeah? Okay. This comes from some orthogonality relationship, but you can because it is like a dummy suffix, because when g dash equal to not equal to g, only this summation is taken. When g dash equals g, this becomes 0. Okay. There are some conditions are there. That is why I am just not going into any of the mathematics, but what is essentially important is that this term is going to be there, na? Each one of these, this is equals to 1 by psi g. So, what it essentially means that extinction distance depends upon, in a particular direction, a g, that is g to g dash means that from one particular value of g vector to another value of g. That tells the periodicity in that direction. For that periodicity, what is going to be the Fourier component of the potential which is going to be there, okay, that is going to decide the extinction distance. You understand that? So, extinction distance directly depends upon the potential within the sample. If the potential is very weak, okay, then what is essentially is going to happen is that the psi g is going to be large, and when the potential is very strong, that psi g is, okay, is going to be small.
But
This is what it happens in the case of, suppose you take aluminium along 111 direction. If you take psi g, you will get a value which will be very high. You take for the same 111, you normalize it by the lattice parameter, because otherwise lattice parameter will be. Take the case of a tungsten. Tungsten, the value of psi g is going to be extremely small, because there the potential is going to be high. You understand that? So, it is related to potential, but the potential itself is not a simple sine wave or a cos wave, it is a complex wave. When it is a complex wave, that potential can be represented in terms of a Fourier series with respect to the Fourier series, but the Fourier coefficients are there, and what is the frequency which we consider? It is with respect to reciprocal lattice vector g, 2g, 3g, like that it will go, various g's which we have to take it.
So here we only account for one diffraction, right?
This is with respect to this g dash can have any value. Okay, this is with respect to each diffraction vector, these values will change. Suppose instead of 111 direction, suppose I take 200 direction. So the value of psi g will be different, because the Fourier coefficient is going to be different. You understand that? And then this term is essentially is nothing but Sg. Sg is the deviation from the Bragg condition. This comes only from this quantum mechanical expression when you write it and try to solve it. You understand that? Okay. Now what I will do it is that, okay, this, if you substitute this Sg and this psi g which we put it, okay, and if you do some substitution, we will be getting explained what is this term which it tells. What we have written is that the rate at which the amplitude of the diffracted beam varies in the z direction depends upon the intensity which is scattered in that direction, the amplitude of the wave scattered in that direction, plus this corresponds to the g dash, means the amplitude of the waves which are scattered in the other direction with psi g, they both have an effect, correct. That is what we qualitatively talked about also earlier. Okay. Finally, under a two beam condition, we will be getting an expression like this, that is the rate at which the amplitude of the wave, that incident wave, you look at it, it enters phi 0. As it passes through the sample, the rate at which it decreases is given by this expression. It can be derived from here, and the rate at which it amplitude of the scattered wave changes, and here we have taken only one diffracted wave and the transmitted wave. Okay. This is what essentially this expression. This expression we can substitute for phi g into this one. If we try to do it, we will be able to write a differential equation like this. This I am not going to any of the derivation, but generally if this sort of an equation which is there, what is the general solution? This all of you have studied in mathematics. No, this will be into e to the power of 2 pi I some alpha into, so that sort of an expression which you write it. Now you substitute and try to solve it. Okay. These are just the mathematical, I am just only showing some of the important results. When you do it, this will turn out to be a term like this with respect to gamma. The solution of this term, because that gamma is essentially contributing to a phase factor, it is something similar to S. Okay. This will have two solutions, okay, gamma 1 and gamma 2. Okay. And if you take gamma 1 plus gamma 2, that turns out to be S, the deviation, and if you take the product of gamma 1 and gamma 2, that turns out to be that 1 by psi g squared. That is why these two terms are very important. These are all coming out of this mathematical operations when you do it. Okay. And then there are some expressions by which it can be written as called. These are all mathematical manipulations, and using which we can find out, because in this what we require is gamma we know, but see what is the ratio of C0 to this one, that amplitudes also we should know. Na? So that everything is being derived in this way. Finally what happens is that when those sort of amplitudes are derived, this is the term which we will have. Na? We said the two beams only are there. That means that psi t will be equal phi 0 into e to the power of 2 pi I k dot r plus phi g into k plus g into dot r, correct. This is how the expression will be. This phi g, when it is being derived, this is a sort of an expression which comes. Okay. You forget. Finally, it turns out to be an expression that phi g squared will turn out to be pi t by psi g the whole squared sin squared pi t s effective by this factor. This expression, if you see it, is very similar to this expression, correct, for the kinematical theory, but the meaning of the terms are quite different. This S effective turns out to be root of S squared plus, now all the derivations I had left out because it is a lot of mathematics which is there, which is unnecessary, but what you should remember is that this is how the intensity of the diffracted wave is going to be, okay. And when S becomes 0 also, this will become 1 by psi g squared, correct. So, you can substitute for S effective into it, then you will find that there will be a fluctuation which will be taking place. Is this clear? Okay. And what will be the intensity of the transmitted wave? It will be 1 minus Ig. Okay. This is the way a calculation can be done. Then the whole issue then comes is that practically when you have to do a calculation, what is the size which you take of that sample dimension? Okay. Suppose I wanted to find out at the back of the sample at this particular point, what is going to be the, what all beams which will contribute to the intensity here. Okay. Suppose a beam is entering here, okay, and the beam should come out through this. As the beam enters, the beam gets scattered, okay, and it is getting diffracted back into this one. So, essentially the diffracted beam makes some angle theta, okay, is it not? And with respect to the lattice parameter, that tells us that if this angle is 2 theta b, okay, all the beams which are falling here in this direction, they will contribute to some intensity or the other to it. Okay. So, that means that at this point intensity depends upon not from only just from this, because the theory we derived it on that basis, but practically it is going to be from these regions as well. So, that has to be taken into account. Okay. Why I am telling is that these assumptions are already, softwares are there where these calculations are being done, they take this into account. This is called as a column approximation. Okay. Then what is normally done is that generally you assume that some thickness of the sample you take it. So, along this column within this, whatever is the beam which is going to enter into it, that will contribute to the intensity at a particular point. Okay. If we know this, what is the value of theta b normally in the case of a sample, in a TM sample, especially it is about less than half a degree. Okay. If it is half a degree, if I assume that the sample size is about 100 nanometer, okay, this diameter will turn out to be about something like 2 nanometers. So, in most of the sample, the column size is taken to be 2 nanometers for the calculation. Okay. This is how the calculation is being done. Okay. Now, let us come back to it. This derivation which we have done, that is what we have started with, is assume that what is the potential of the sample we know, the wave function, what is the wave function when we write it as the exponent, that tells us nothing but what is the path which the electron is going to take as it moves within that sample. In the physics term, we will call it as a wave function, chemistry we will call it as an orbital function, right. What is the orbit which it is going to take, correct. So, that is what we have done it. That depends upon, that wave function, the sample depends upon what is psi g. It is essentially with respect to the beam directions, right. With respect to a beam which is there in the transmitted direction, what is it going to be the amplitude of the wave, phi 0, phi g is the amplitude of the diffracted wave. Okay. So, the path of the electron within that sample is being controlled by amplitude of the transmitted beam as well as the diffracted beam, okay, and that it is related to the potential which is being potential of the electron comes in terms of that psi g, correct, okay. And this is the equation. When we solved it, we arrived at for phi g an expression like this, okay, and this is how we have got that final expression, okay. Now when s becomes 0, what this will turn out to be phi, this will become pi into t by psi g, correct. Then phi 0 squared will be here. Now what is going to happen is that as the thickness of the sample t by psi g becomes 1 half 3 by 2 2 like that, the intensity is going to fluctuate it, okay. That is what is being seen when s equals 0. So this expression, the dynamical theory of expression, is now able to explain all the experimental observation, okay. Not only that, suppose S effective is there, then like the way we explained it for the kinematical theory, S effective and T we can take it, is it not? The way we explained in kinematical theory, when the S is going to be very large, then what is going to be this 1 by psi g is going to be the psi g will increase, okay, that this term will become 0, S effective will become yes, then the kinematical theory is valid. So this theory has, it is a theory which explains under all conditions how the contrast will vary, whereas the kinematical theory can explain when the deviation from the Bragg angle is large, but not when not under exact Bragg condition. Is it clear? Okay. So this is where a table which I am showing it for different diffraction, this one for 100 keV electrons, what is going to be the psi g value which has been calculated for s equals 0, okay. What is going to be the effect of this? The effect of this will be that suppose you have a multi-layer sample in which each layer has got a different element which is being present there, or the composition from layer to layer changes, then the psi g will also change. The effect of the psi g will be that even under the condition when s equals 0, if the closer to the thin file, closer to the hole of the sample, because generally any of you have prepared samples for TM? What is the shape it looks like? It is a hole, sample looks like circular, but the thin region, it is a hole, from here it goes. So it is essentially, it will be something like, this is how it is. So it is essentially a wedge shape which is going to be there, correct? Even under the Bragg condition, okay. So if there is, it is like a multi-layer when it is going to be there, psi g will vary locally, that will have that effect on this periodicity of these bright and dark fringes. That is what you can see it here. You see this is gallium arsenide, this is aluminum gallium arsenide. Now you can see that how the fringes are changing, okay. So gallium arsenide has got a higher this one, so fringe spacing. So here you see that when the aluminum is introduced, the fringe spacing has changed, correct. So all the features which you observe could be, there are many situations where you will not be directly able to interpret it, the image content. Then under those conditions, that we will take it up in the next class. I will explain some cases where we have done it, okay. Computer simulation of the image which you have done it to verify it, okay. In such conditions, you have to do simulation to find out, for which you should understand all these theory. Software will be there, but you should know how to use it, how to optimize it and use it. For that, unless you understand the theory, it is going to be difficult. If somebody wants to do a serious microscopy, anything which we do, otherwise we are not sure what we interpret is correct or not, okay. So this equation which we have written for the variation of incident amplitude of the incident beam and the diffracted beam. This is called as the Hovey-Whelan equation or Hovey-Whelan-Darwin equation. Okay. This equation is for a perfect crystal. When it is going to be a crystal with a defect, like the way we have seen it, wherever that SZ is going to be there will be a term which will be attached, SZ plus G dot R, where R is going to be the defect vector. Exactly this term will come. Like in that case, if the G which we choose is such that G dot R becomes 0, then it becomes a case of perfect crystals. So in fact that is used to find out the Bijus vector of the dislocations. Okay. And then about strain contrast around precipitate, all these things will be determined by this G dot R. Okay. Some examples, now I had just given the formalism, okay, the mathematical derivation. Without going into it, I said that what is the need for a dynamical theory, from the kinematical theory, how the dynamical theory differs, okay, just had written the initial expression and the in between this expression which comes, and what is the relationship of psi g with respect to the periodic potential, all these things, some expressions which comes out of it, only just the expression which I had flashed. Okay. In the next class we will take it up, because when we do the calculation all these things have to be put into a place and we have to do it. That is why I had introduced this. Okay. In the next class we will take some few examples of defects which both with kinematical and dynamical, how we try to interpret it, that part we will take it up. Okay. We will stop here now. Thank you.